So this is the last video for the waves unit where I'm going to talk about diffraction today. So diffraction is what happens when a regular wave goes through an opening in a boundary. So we've got this diagram here and we're trying to think about what would happen afterwards in terms of, does the wave just keep going straight? Does it turn? Does it do anything unexpected? So to see that, let's go to the simulation here, and once we start it, that answer will be solved. So what we see here, and just so you can see everything, is we've got a plane wave coming towards a boundary, such as a wall that has an opening in it to allow some of the wave to go through. But what we see from the wave is a really interesting property, that it starts turning. So it bends around the corner, which is really interesting. And then it goes straight once it gets around the corner, but it can turn and follow the wall, and parts of it goes straight. So, and there's some other interesting things that go on here. So there's some different types of interference resulting, because now the wave is going out in a circular pattern. But what we see is the wave actually bending and spreading out again instead of going in just one direction. So we can draw this on our diagram with, just drawing our wavefronts and curving them out as they've gone through our opening. And this is what diffraction is. So we have the diffraction is the bending of waves as they pass through an opening or around the edge of an obstacle. And which we can see here, we go from a plane wave traveling in one direction, and but starts spinning. And what we can do is, if I add in, another wall over here with another opening, we should see the same thing start happening, and we can see it again there, where the wave spreads out through the other opening. Don't worry about the stuff at the top, because it starts getting very complicated with the different directions that the waves are now reflecting and interfering with each other. But all we want to focus on is how the wave spreads out through an opening. And that is called diffraction. Now, in terms of diffraction, there are some things that don't change as the wave goes through the opening. Most importantly, the wavelength doesn't change, which means things like it's not changing in medium, it's not going to refract, so there's no change in frequency or speed, and so the wavelength isn't going to change as well. And that makes sense. There's nothing affecting the wave, it's just going through an opening, and that opening changes the direction that the wave is going, not the properties of the wave itself. But the wavelength does affect how much diffraction happens, as does the size of the opening. So if we go back to the simulation here, if we start the wave, we can see it going there, and I can draw in a wall. If I draw a wall over here with a fairly large opening, and then I do a small opening on this side, we should be able to see the difference. And right away, we can see that for the most part, this wave it's diffracting a little bit, but not nearly as much as the one with the small opening. So the smaller the opening, the more the diffraction. So more diffraction, not for more, a smaller opening gives us more diffraction. Now, in terms of wavelength, we see something different happen. So if I start this here, we will have a longer wavelength of this wave, and as I put in a That's not the wall that I was hoping for. And clear the waves. If I put in a wall with a small opening, we saw how it diffracted before, which is fairly significant, and we let it play. We see it's very significant amount of diffraction here. It's going all the way out this far. And now if we clear the wave, put the frequency back up, and play the wave again, it's not diffracting as much. There's a lot less going on in these areas over here. So more diffraction happens with longer wavelengths. Now physicists always like to combine things, so once they figured out what happened with one slit, they said, well, what happens if the wave is going to go through two slits? What's it going to look like? So now we've got a plane wave going towards two slits, and they know that at each one it's going to start diffracting, which we can see in the simulation. So now our border's got two slits in it. We know each one is going to diffract. So when we start the wave, and maybe increase the frequency a bit here, there's some interesting characteristics that end up happening. And now we can start to see it nice and clearly. So when I stop it there, there's some visible lines that we can see. So if we think about having two waves, they're going to be interfering. Now these lines have no wavefronts shown on them, and that's because there's destructive interference where the waves are canceling each other out. And that produces a very interesting pattern, which we can see on the next page. So we have this waves that are diffracting and they start interfering. Crest and trough start combining all over the place. And we get a pattern that looks often like this, where we see periods of maximum and periods of min. So high points and low points and points with no wave whatsoever. And this concept of interference patterns through two slits was used by Thomas Young to explain, in their view, in 1801, that light was a wave by doing this experiment with light. And we'll see that later on when we actually will try and replicate this experiment with light and through two slits. But for us, that's all we're going to study on topics of waves. So we talked about the wave speed, the wave equation, reflection, interference, refraction, diffraction, interference patterns, and so that's the culmination of unit number 7. So as always, physics is awesome.